All right, so today we will wind down on the setup of the scattering problem, and then we will try and work out one example, which is a standard textbook example of scattering from a hard sphere. So this is also something that we understood classically when we began our lectures on scattering. Okay, so first let us briefly recap where we are. We have developed a formula for the scattering amplitude, which you see right above, right? So f of theta can be written in terms of the Legendre polynomials PL of cosine theta. Okay, so sometimes the methodology that we are discussing right now goes under the name of partial wave analysis. Partial wave analysis because we are decomposing the scattering amplitude in terms of many different values of L. Okay, for example, L equals 0 is called the S wave, and L equals 1 is called the P wave, and so on and so forth. Sometimes it is also called the phase shift analysis because essentially calculating f of theta is tantamount to calculating the phase shifts delta L, right? So the goal is to calculate the phase shifts and thus f of theta. Okay, and knowing f of theta, of course, we know everything about the differential cross section, which is the quantity we now turn to. So the differential cross section d sigma d omega, where d omega is a solid angle omega subtended at the site where you're measuring the particles, the amount of particles that have been scattered in some solid angle d omega. This, as we discussed, is the absolute modulus of f of theta quantity squared, right? So I will take the definition of f of theta that we developed earlier, L equals 0 to infinity. This is basically writing f of theta in terms of the PL of cosine thetas. Of course, we later found out that the FL is basically e to the 2i delta L minus 1 divided by 2i, which is basically a statement about the scattering matrix being unitary. And let us plug in this definition of f of theta in our formula for the differential cross section. So d sigma over d omega. So f star, remember that the coefficients FL can be complex. Of course, the Legendre polynomials are manifestly real. So if I do this expansion out, L prime, 0 to infinity, I'll have a factor of 1 over k square from the 2f of thetas, a 2l plus 1, a 2l prime plus 1, and FL prime star, FL, PL prime of cosine theta, PL of cosine theta. Okay, and that looks like a rather unwieldy formula, but I promise you it will simplify once you calculate what the total cross section is. And by the way, if you have any questions, please stop me and ask. Okay, so what is the total cross section? The total cross section, sigma total, is looking at the number of the scattering cross section per solid angle integrated over all such solid angles. So this is equal to, now since I'm only integrating over the solid angles, I'll pull out everything that is not a function of theta or phi outside the integration. So this is L prime 1 over k square. K square is just the incoming momentum, which is a constant. FL has nothing to do with the angle. The only thing that depends on the angle is d omega PL prime cosine theta PL of cosine theta. Okay, and this, as you know, can be easily evaluated by appealing to the orthogonality of the Legendre polynomials. So since there is no phi dependence, integral d omega, which is integral d phi from 0 to 2 pi and 0 to pi d theta sine theta, and by making a change of variables omega equals cos theta, this can be written as 0 to 2 pi integral d phi minus 1 to 1 dw. Okay. So, and I can integrate the phi trivially because there is no phi dependence anywhere. So, my formula for the total cross section now becomes L prime 1 over k square FL. I'll pull out a factor of 2 pi from the angular integration of phi. So the remaining stuff I have is minus 1 to plus 1 dw PL prime W, because my cosine theta has been relabeled to W, PL of W. Okay. And this, you know, from the orthogonality of the Legendre polynomials is equal to 2 divided by 2L plus 1 delta L prime. So if I substitute this result, I find that the two summations over two different values of L essentially boil down to just one summation. So sigma T is now given by sum over L equals 0 to infinity 1 over k square. There is two factors of 2L plus 1 and there is a factor of 12 plus 1 in the denominator. So one factor of 12 plus 1 cancels. And there is a 2 over here and the 2 pi over there. So these both combine to give me a factor of 4 pi. And everything that is remaining is basically modulus FL square. Okay. And noting that FL can be written as e to the I delta L sine delta L. Modulus FL is basically just sine delta L, which gives me a nice compact formula for the total cross section. Sorry, there is a factor of 2L plus 1 that I missed. Sigma T is 4 pi over k square L equals 0 to infinity 2L plus 1 sine square delta L. Okay, so this is a fairly important formula. So I'll box this. This is basically a straightforward application of the formula for f of theta that we have developed using the orthogonality of the Legendre polynomials. Are there any questions about this? So basically, the formula for the total cross section is written as a sum over the individual L modes. So if I denote by sigma L the quantity 4 pi over k square 2L plus 1 sine square delta L. This is the scattering cross section for an incoming wave with momentum, angular momentum L, little l. Okay. So the total cross section is given by the sum of all such partial waves. Okay, scattering of all such waves. Now, it might seem like this is an impossible thing because we have to calculate an infinite number of delta L's, but I will make a sort of a hand-waving argument as to why that is usually practically not the case. Now, remember that each one of these sigma L's is actually bounded because sine square delta L is bounded by 1 for delta L equals pi over 2. So sigma L, each sigma L has to be less than or equal to 4 pi over k square times 2L plus 1. Okay, so this is sometimes called the unitarity bound. So the cross section for every single one of these partial waves is bound by some value which is given by 4 pi over k square times 2L plus 1. Okay, because sine square delta L is bound by 1. So I can understand the total cross section as the sum of all such partial waves. Okay. Now there is another nice way in which one can understand this sigma total. So to understand what this means, let us again go back to our definition of f of theta. What is f of theta? I will write f of theta as L equals 0 to infinity 2L plus 1 over k FL PL of cosine theta, right? Now, what exactly is happening? I am throwing a particle towards the scattering center, right? Now I'm going to write this incoming plane wave as a series of uh, incoming and outgoing spherical waves with various different values of L. And each one of these incoming waves with various different values of L is going to be scattered, and you're going to get a whole bunch of scattered spherical waves. And of course, since the scattering center of the potential is a rotationally symmetric potential, it's not going to do anything to the value of L. So if I send in a wave with L equals 2, the scattered wave corresponding to this guy would also have L equals 2. The only difference would be that there will be a slight phase shift given by delta L, okay, in the scattered wave, which is what I want to measure. Now, the incoming wave that I'm throwing in is in the forward direction. What is the forward direction? The forward direction is theta equals 0, okay? Of course, if all the outgoing waves also have theta equals 0, it means that there has been no scattering, right? So that is a very trivial case. Of course, the waves are scattered in various thetas. So in other words, in various solid angles. So basically, if I throw in a wave in the forward direction at theta equal to 0, then after scattering, the amount of wave that I should measure in the forward direction should be less. Okay, so this point is important, and it is actually a fairly straightforward point to make because the waves are being scattered. If I throw in a bunch of waves with various different values of L with theta equal to 0, then these are all going to be scattered at various different thetas, and it is possible that some of them are not scattered and go along in the forward direction, but most of them are going to be scattered, right? So the amount of wave I find in the scattered part along theta equal to 0 should be less, okay? So in other words, if I measure the amplitude in the forward direction, the measure of amplitude in the forward direction should tell me something about the scattering cross section, because the total amount of scattered waves in the forward direction should be reduced, okay? We will do a tutorial problem that explains this concept a little bit more, but roughly speaking, it is not unreasonable to expect that there has to be some relation between the scattering cross-section sigma and the amount of stuff that is scattered in the forward direction. Okay, so this is a relation that we will develop. It's actually fairly straightforward to develop, and it has a fairly rich history, and it goes by the name of optical theorem. So what is the optical theorem? To understand what the optical theorem is, let us first write down the scattering amplitude in the forward direction. So if I put in theta equal to 0, PL of cosine theta is just PL of 1, because cosine 0 is 1. And for any value of L, this is just 1. So if I write down the scattering amplitude in theta equal to 0, this is simplified to 2L plus 1 over K FL. Okay, the PL of cosine theta is simply equal to 1. So what is this? This is equal to L equals 0 to infinity, 2L plus 1K. FL is e to the I delta L sine delta L. So I can write this as this. Okay, so which means the real part of f of 0 is given by 2L plus 1 over K cosine delta L sine delta L, and the imaginary part of f of 0 is given by 2L plus 1 over K sine square delta L. Okay. Now, if you compare the imaginary part of the forward scattering amplitude to the total cross section, you would find that apart from a factor of 4 pi and K, it's exactly the same thing. Okay, there is a sum over 2L plus 1 sine square delta L. There is also a sum over 2L plus 1 sine square delta L. So I can actually write that the total cross section sigma T is 4 pi over K times the imaginary part of the forward scattering amplitude. Okay. This is called the optical theorem. It's called the optical theorem because it was first derived in the context of wave propagation in terms of light, Lord Rayleigh discovered that there is a corresponding formula in the case of light, and there it has to do with the imaginary part of the refractive index of the medium. Anyway, there is a corresponding formula in the quantum mechanical version also. It simply states that the total cross section is 4 pi over k times the imaginary part of the forward scattering amplitude. Okay. So this is the optical theorem. To understand a little bit more about the physics of this optical theorem, we will develop a tutorial problem that should help it explain it a little bit better. Okay. So what have we done thus far? So our job basically was to develop one particular way of looking at the scattering problem. And we looked at the scattering problem by basically decomposing the incoming and the outgoing waves in the angular momentum basis, right? So what we did was basically do what is called a partial wave analysis, wherein we took the incoming and the outgoing waves, broke them up in terms of the Legendre polynomials, wrote them down as a series. And then we said that, look, calculating the differential cross-section is tantamount to calculating the scattering amplitude. And then we went a bit further and argued, based on the unitarity of the S matrix, that calculating the scattering amplitude is tantamount to calculating just the phase shifts. Okay, now this still leaves us the question of how many different phase shifts that we have to measure, because we can decompose an incoming plane wave into an infinite number of angular momentum eigenstates. But it turns out that practically speaking, this is not necessary. Okay, so I will develop a rough semi-classical hand-waving argument as to why this is true. So remember that when we set out the scattering problem, we threw the particle at some distance from the axis, and this distance, vertical distance, was called the impact parameter, right? So, excuse me. So, and this distance we called B. Oh, sorry, this is not showing up. So let me stop share and reshare it. Okay. Now, suppose if this guy has a momentum B, classically speaking, the classical angular momentum of this guy is going to be PB, right? R cross P. So momentum is in the forward direction. So the P is in this direction. B is measured in the vertical direction. So R cross P has a sign pi by 2, which is 1. Okay, so classically speaking, the momentum should be is something like PB, right? Now, if the scattering center has a range, some typical range, let's call the range of the scattering, some, let us say, R0. Okay. Now, if the impact parameter is much larger than this R0, of course, then only that part of the incoming beam of particles that is looking at R0 will get scattered. The rest of them would be immune to scattering because it won't feel the effects of the potential. Okay. So there is as I mentioned in the beginning stages of the discussion on scattering, there is an intimate connection between the impact parameter and the range of the potential. Now, if I want to do a quantum mechanical analysis, I'll just hand wave and say that this angular momentum is quantized in some units of h bar, so h bar L, right? And this has to be equal to P, can be written as h bar KB. Okay, so which means that the impact parameter B, if it is much greater than R0, then, so I can turn this into an equation for B as B is basically L divided by K, right? Now, remember that this is not the correct quantum mechanical formula, h bar times L. I'm simply assuming that this quantized in units of h bar L, but you know that the eigenvalues of L square are h bar square times LL plus 1. But forgetting all these simple factors, basically I'm claiming that if this B, which is L over K, is much larger than R0, then there is going to be a whole bunch of particles that is not scattered, right? So which means this bound on B that ensures a scattering of all particles can be in turn turned into a bound on L that ensures that all particles are being scattered, which means there is always an L max, which is roughly of the order of K times R0. And beyond this L max, I really don't have to worry because there is no scattering happening for these particles. Okay? So typically in a typical scattering problem in quantum mechanics, it turns out that you don't have to measure the phase shifts of from L equal to 0 to L equal to 220. It is usually the case that, for example, an S wave analysis is sufficient, or at most the L equals 0, the P wave analysis, because going beyond that in general is quite tedious and in most cases completely unnecessary. We will substantiate this argument now, even if you don't buy this hand waving argument, by doing a particular example of hard sphere scattering, and we will explain what this particular bound means. So before I do that, are there any questions? Any questions or any comments? Hard sphere.
सर सर ये अपन ने ऊपर एच कट एल लिखा है वो क्या है मैं समझ नहीं पाया सर.
So this is basically just a rough way of understanding. Suppose if I have a classical angular momentum P times D, I'm simply claiming that the corresponding quantum mechanical angular momentum is quantized in units of h bar. Okay, so this is not a very correct way of looking at things. It is just a rough way of motivating this bound. Okay. So basically all I'm saying is that in quantum mechanics, L doesn't take a continuous value. It is quantized in units of h bar. That is all. There is nothing very deep about whatever I'm doing. Okay. Anything else? Okay. All right. So let us look at hard sphere scattering. So remember that this is the example that we did initially when we started out scattering, which a few lectures ago. Sorry, I could go back. So when we developed the notion of scattering, we gave an example of hard sphere scattering, which turned out to be pi r square, right? So we will again revisit the exact same problem, but this time using quantum mechanics and employing partial wave analysis to do the problem. Okay. So what is hard sphere scattering? The potential is such that V of R is infinity when R is some less than A, and is 0 R greater than A, where R is some radius, right? So there is no way the particle can penetrate the sphere, because inside the sphere the potential is infinite. Of course, outside the sphere the potential is 0. Which means inside the sphere, the wave function for the particle should be 0, and outside it can be anything else, which means for continuity of the wave function, we should also demand that psi of A should be equal to 0, right? So this is the boundary condition in the problem. So let us actually develop the solution for scattering. So basically I have a sphere, a potential, which is just a infinite potential inside this region, and I'm throwing a bunch of particles at it, and then I'm going to understand how the quantum mechanical scattering proceeds. Okay, this is the rough picture. There cannot be anything inside the sphere, because there is corresponds to an infinite amount of force. Okay. So in the R greater than A region, remember that we are solving the three-dimensional Schrodinger equation. I can always write my solution psi of R comma theta as L equals 0 to infinity RL or R PL of cosine theta. Okay, so this is exactly what we did when we solved the three-dimensional Schrodinger equation. Of course, we used spherical harmonics YLM of theta phi, but in this case, since there is no phi dependence, because we are looking at spherically symmetric potentials, we only have to contend with the Legendre polynomials PL of cosine theta. So let me set up the radial Schrodinger equation. I'll just quote the result in this d rho square minus L plus 1 over rho square plus 1 rho RL of rho equals 0. Okay. So remember this term from your quantum mechanics notes last time. So this is called the centrifugal term in the potential, right? So there is a repulsive term in the potential. This has nothing to do with the external potential. This comes in when we write down the del square operator in spherical polar coordinates. Because you're looking at common eigenstates of the Hamiltonian and the L square operator, when you use that fact, this term automatically pops up in the definition of del square. Okay. Now, if I'm looking at distances very, very far away from the origin, r equal to 0, remember that rho in my definition is k times r. So instead of using r, I'm using the variable rho. Now, if I look at rho going to infinity region, then the solutions RL of rho is e to the I rho over rho. Okay, so these are the spherical waves that we discussed. If I don't want to look at infinite rho, if I want to look at any finite rho, of course, I'll have to solve this differential equation, which I will not do, but I will tell you that the solutions of this differential equation are what are called spherical Bezel functions. So just like a second order differential equation, for example, you have seen differential equations that are exponentially growing or exponentially decaying, like e to the lambda x, e to the minus lambda x, or oscillatory, e to the ix, e to the minus ix. This equation also has two classes of solution. The two classes of solution are JL of rho and eta L of rho. Okay, see, these are what are called spherical Bezel functions. Okay, so these are neither exponentially increasing or decaying, or neither they are oscillatory. They are sort of mixed between the two. Okay, they behave like oscillatory functions that are actually decaying. So there is a mathematical formula for the JL and the eta L. JL of rho. So my handwriting is such that my L and rho look alike, but L is always a subscript and rho is always the argument. So in case you're confused, please remember this. L is always a subscript and rho is always an argument in things like JL of rho. This can be written as minus rho to the L 1 over rho d rho to the L sine rho over rho. Okay. Similarly, eta L of rho is, these are all standard formulas that you can find in any textbook, minus rho to the L again 1 over rho d, this time cosine rho over rho. Okay. So even though the general formulas look a little complicated, what we are really interested in is looking at the various limits. The two limits that we are going to look at specifically are the asymptotic limit, where rho goes to infinity, and rho goes to 0. We also want to look at the limit where the argument of the spherical Bezel functions is very small, because we will need this expansion also. So let us look at these two limits. So in the limit that rho goes to infinity, the JL rho becomes sine rho minus L pi by 2 divided by rho, and eta L of rho becomes minus cos. Okay, so this is in the limit rho goes to infinity. And in the limit rho goes to 0, they have completely different properties. So in the limit rho goes to infinity, one looks like a sine rho over rho apart from a phase, and one looks like a cosine rho over rho. So they sort of look alike, okay, in some sense. But in the limit rho goes to 0, they behave quite differently. JL of rho goes to rho to the L divided by 2L plus 1 double factorial, and eta L of rho goes to minus 2L minus 1 rho to the minus of L plus 1. This is in the limit rho goes to 0. You see, so the double factorial simply means, so this is also a double factorial. 2L plus 1 double factorial simply means that the product of all odd numbers up till 12 plus 1. Okay. Just like the factorial is a product of every number till that particular number, a double factorial is the product of all odd numbers till that particular number. Since L is an integer, 12 plus 1 is of course an odd number. Okay. So you actually see that as rho goes to 0, JL is regular because it goes to basically 0, but eta L blows up. So you have to be careful in constructing these functions and understanding their properties as rho goes to 0, because eta L goes like 1 over rho to the L plus 1, and as rho goes to 0, this function diverges. So you have to be a little careful. So JL is regular, eta L is not at the origin. One aside that I need to make at this point, which is not intimately connected to what we are going to discuss, but it is something that you would find in every textbook. So I need to make sure that you understand this. Remember that a couple of lectures ago, we wrote down the incoming plane wave, which is e to the I k r cosine theta, which in our language is with regard to our variable is e to the I rho cosine theta. We wrote this as L equals 0 to infinity, 2L plus 1, UL of rho, PL of cosine theta, right? So we argued that since this is a function of angle, I should be able to express this in terms of the basis functions PL of cosine theta, right? And then we developed a formula for UL of rho. We also developed a formula using partial integration by parts and by exploiting the orthogonality with the Legendre polynomials. We argued that UL of rho should be equal to 1 over 2 I rho e to the I rho minus 1 to the L e to the minus I rho. And then we said that since we are looking at distances very, very far away, we're going to throw away factors of 1 over rho square. Right? So if we go back maybe a couple of lectures, we should be able to find this. Give me just a second. So there it is, right? So this is exactly what I'm talking about. So e to the I k r over r, k times r is rho. So this is of the form e to the I rho over rho minus 1 to the L e to the minus I rho over rho. So there is a way to understand this formula using the spherical Bezel functions and using the asymptotic properties that we have just discussed. So let us write this as, so I can write minus 1 to the L as e to the I pi L, right? Because e to the I pi is minus 1. So UL of rho can be written as 1 over 2 I rho. I'll pull out a factor of e to the I pi L over 2, and I will write this guy as e to the I rho e to the minus I pi L over 2 minus e to the I pi L over 2 e to the minus I rho, which means this entire thing can be written as 1 over 2 I rho e to the I pi L over 2 times e to the I times rho minus L pi over 2 minus e to the minus I rho minus L pi over 2. So this is just some simple algebra. And when all is said and done, you recognize that whatever is multiplying the inside the parenthesis divided by 2i is just the definition of sine. So this can be written as e to the I pi L over 2 times divided sine rho minus L pi over 2 divided by rho. And this is e to the I pi over 2 is just I. So this is I to the L times sine of rho minus L pi over 2 divided by rho. But if you actually go back and look, this is exactly the asymptotic nature of JL of rho. So these functions UL of rho, which are the coefficients of the different angular momentum components of a plane wave, are nothing but the spherical Bezel functions in the asymptotic limit. So I can write this as basically JL of rho. Okay. So in many textbooks, you would actually find that they write this e to the I rho cosine theta as L equals 0 to infinity 2L plus 1 I to the L JL of rho PL of cosine theta. And the reason is exactly what we just discussed. The formula that we developed is exactly the asymptotic form of the spherical Bezel functions. Okay. Anyway, so now back to the hard sphere scattering. Is there any questions about this? So you can equally well use this UL, whatever that we have discussed. What is this UL? This guy. Or you can use in a more compact fashion just JL of rho. So it's exact same. Okay, so back to hard sphere scattering. In the R greater than or equal to A regions, I can write down the radial wave function RL of rho as AL cosine alpha L JL of rho minus sine alpha L eta L of rho. Okay, basically all I'm saying is that the radial wave functions is some linear combination of JL and eta L. Okay, so for example, Shankar would say that RL of R is AL JL of KR plus BL eta L of KR, which is exactly the same thing. Okay, so instead of calling the two integration constants AL and BL, we have called the two integration constants AL and alpha L. Okay, so that is all. This is just a change in notation. That is all. So the question is, what is alpha L and what is AL? In particular, what is alpha L? Okay, so this would be your homework, and we'll also revisit this in the tutorial if you have a hard time understanding this. The way to understand what alpha L is actually, so remember that then psi of r comma theta in this case turns out to be L equals 0 to infinity AL cosine alpha L JL of rho minus sine alpha L eta L of rho times PL of cosine theta, because psi of r comma theta can be written as, this, right? It's a linear combination of the Legendre polynomials. So RL turns out to be a combination of spherical Bezel functions. So the total wave function is spherical Bezel functions multiplied by a PL of cosine theta. To fix alpha L, we need to compare the asymptotic nature of this wave function with the general asymptotic wave function that we have developed. What is the general asymptotic wave function we have developed? Remember that asymptotically, so let us call this equation 1. Asymptotically, we expect psi of r equals sum over L, 2L plus 1 over K, this is Ronsard's, minus 1 to the L plus 1 e to the minus IKR over R plus 1 plus 2 IFL, or rather 1 plus 2 IFL can be written as, there's also a factor of 2I here, I think, e to the 2I delta L e to the IKR over R, right? So this we'll call equation 2. Now take the asymptotic limit of equation 1. Okay, this is our general understanding of scattering that if I look at very regions very far away from the scattering center, my wave function for whatever scattering that I'm doing, my wave function should look like equation 2. Now, for this specific case of hard sphere scattering, our solutions turn out to be equation 1. So let us look at equation 1 in the region where r goes to infinity, okay, or in equivalently rho goes to infinity. So look at the asymptotic limit of equation 1. What would the asymptotic limit of equation 1 be? So RL of rho is cosine alpha L JL of rho minus sine alpha L eta L of rho. In the asymptotic limit, rho goes to infinity, J behaves like sine rho minus L pi by 2 over rho, and eta L behaves like cosine rho minus L pi by 2 over rho. So this, the limit rho goes to infinity using the asymptotic nature that we have just discussed, which is over here, right? This one. Substituting this, we find that this is equal to cosine alpha L sine rho minus L pi by 2 divided by rho plus sine alpha L cosine rho minus L pi by 2 over rho, which means in this limit, this goes over to 1 over rho times sine of rho minus L pi by 2 plus alpha L. Okay, so let us call this equation 3. Now, if you actually compare equation 3 and equation 2, you remember that you can also write equation 2 in terms of the signs using the same trick that we just discussed here, right? So pull out a factor of e to the I L pi by 2, and you can write the exact same thing as sine rho minus L pi by 2. So I will leave this to you as a homework. Check. Comparing equations 2 and 3, we can deduce that the integration constant alpha L that we have been talking about is nothing but the phase shifts delta L. Okay, so this is your homework. Okay, so please take this seriously and complete this. You can actually show by looking at the asymptotic form of the general wave function to the asymptotic form of the specific wave function for this particular problem, and compare the two, and you'll find that alpha L, the integration constant, is nothing but delta L. Okay, so which means I can write my my solution for this problem, psi of r comma theta, is L equals 0 to infinity AL times cosine delta L JL of rho minus sine delta L eta L of rho PL of cosine theta. Okay. Now, I should also have that the boundary condition should be satisfied. Psi of A has to be equal to 0. If psi of A has to be equal to 0, this means that, remember that rho is K times R. So if I substitute psi of A equal to 0, the only way this can be equal to 0 is if cosine delta L JL at Ka, the stuff inside the parenthesis, minus sine delta L eta L of Ka should be equal to 0. And this gives you a nice way of determining the phase shifts delta L. Tan delta L is equal to is it plus or minus? Tan delta L is JL, excuse me, JL of Ka divided by eta L of Ka. Formally, this solves our problem. So one can always use this expression to calculate the phase shifts. Knowing all the phase shifts, we know the scattering amplitudes, and knowing the scattering amplitude, we can calculate the differential cross-section. Okay. Formally, this is the solution. But of course, we can go ahead and understand this physically, making some approximations. So let us look at the L equal to 0 partial wave. So L equal to 0, what does this equation tell you? At L equal to 0, tan delta 0 is J0 Ka divided by eta 0 of Ka. Okay. But you know exactly what J0 of Ka and eta 0 of Ka are. For L equal to 0, the Bessel functions are quite simple. For J equal to 0, this is simply sine Ka divided by Ka, and eta 0 is minus cosine Ka divided by Ka. One way to see this is by looking at the general formulas for the spherical Bessel functions, which we have written here, right? And put an L equal to 0. If I put L equal to 0, of course, there is no differential operator acting on it. And JL would be simply equal to sine rho over rho. And eta L would be equal to minus cosine rho over rho. Right? So this is fairly straightforward to see. So the L equal to 0 scattering is fairly straightforward. Tan delta 0 is simply minus tan Ka, which tells you that the phase shift for the L equal to 0 waves is nothing but minus Ka. K is the momentum and A is the radius. So, K is more correctly the wave number, right? So this is a dimensionless number as it has to be. Now for the rest of the guys, in general, these JLs and KLs, eta Ls are a little complicated. So you'll have to evaluate the phase shifts. But we can try and understand the nature of these phase shifts by looking at incoming waves that don't have a lot of momentum. So let us work in the low momentum approximations. Up till now, everything that we have done is exact. Suppose if you look in the low momentum approximation. What is this? This is basically saying that suppose if I look at the limit where Ka is much less than 1. Okay. So if I want to compare it to a classical particle, this is exactly what I would say, because I don't throw it with a lot of momentum. So I'll assume that I'm looking at momenta of the particles that are not very large. So if Ka is much less than 1, the argument of the spherical Bessel functions is very small. And in this regime, when the argument of the spherical Bessel functions is very small, we know that JL goes like rho to the L and eta L goes like rho to the minus L plus 1. So using this, we can argue that tan delta L for the higher L modes should be roughly equal to minus Ka to the L divided by 2L plus 1 double factorial. This is the nature of the JL, and Ka to the L divided by 2L minus 1. Sorry, Ka to the L divided by 2L minus 1 double factorial is the nature of the JL. And Ka to the minus L plus 1 divided by 2L plus 1 double factorial is the nature of the eta L. So this whole thing is actually quite suppressed for large Ls. So remember that Ka is also a small number, and for larger momentums where L is high, this is actually quite suppressed. So the phase shifts for larger Ls is actually negligible. So this is also another reason why we can simply work in the S wave and P wave scattering, because for most purposes that is more than sufficient. Okay, so this is actually a proof of concept as to why we typically ignore higher L scatterings, and we typically stick to L equals 0 and 1, at most 2 in very rare cases. So let us actually wind down this analysis by looking at the S wave scattering and calculating the total cross section. What is the total cross section? The total cross section is L equals 0 to infinity sigma L. But if I'm simply sticking with sigma 0, this is 4 pi over k square 2 times L plus 1, L equals 0 for S wave scattering, sine square delta 0. Okay, delta L is delta 0. So for S wave scattering for the hard sphere, my cross section turns out to be 4 pi over k square sine square Ka. Okay. And since Ka is very small in the low momentum approximation, this is approximately equal to 4 pi over k square times. So delta 0 is minus Ka, so I should write this as minus Ka. Okay. Now I will neglect factors. So since I'm expanding sign, I'll neglect factors higher order in Ka and only keep the leading order term in sine square Ka, which is just Ka whole square. So the total cross section in this limit turns out to be equal to 4 pi a square. Okay. Now, if you compare it to the classical scattering formula that we have developed, the classical scattering formula would have given you pi a square or pi r square. The quantum mechanical version for the lowest lying L equal to 0 mode differs by a factor of 4. Okay, so it measures the total cross section for the quantum mechanical scattering is 4 pi a square, while the classical result for hard sphere scattering is just the geometrical cross section pi r square. Okay, so this is one difference between. Usually the quantum mechanical results will vary from the classical results in such simple cases by factors of 4 and pi, and this is one such example. Okay, so we will stop at this point and then we will do more examples in the tutorial problem on Monday. So please do ask if there's any questions, otherwise I'll stop the recording at this point.